When discussing conductors operating above 2000 volts, it's important to consider the voltage reference. The reference point dictates how the voltage is measured and its implications for insulation requirements, safety procedures, and equipment design. While the context does not explicitly state whether the 2000 volts threshold is with respect to ground, it's a critical distinction to understand. Firstly, a voltage with respect to ground, often called voltage to ground, signifies the potential difference between a conductor and the earth or a grounded conductor within the system. This measurement is crucial for assessing the risk of electric shock and for selecting appropriate grounding methods and protective devices. Secondly, voltage between conductors, also known as voltage to voltage, refers to the potential difference between two ungrounded conductors in a circuit. This voltage is essential for determining the power carrying capacity of the conductors and for ensuring proper operation of connected equipment. The specific application and design of the electrical system dictate which voltage reference is most relevant. In high voltage systems, understanding both voltage to ground and voltage to voltage is paramount for safety and performance. For instance, in a three-phase system, the voltage to ground is typically lower than the voltage to voltage. The relationship between these voltages depends on the system grounding configuration, such as grounded Y, ungrounded delta, or corner grounded delta. In a grounded Y system, the voltage to ground is the phase voltage, while the voltage to voltage is the line voltage, which is approximately 1.732 times the phase voltage. Understanding these relationships is essential for selecting appropriate insulation levels for conductors and equipment. When working with conductors operating above 2000 volts, stringent safety precautions are necessary to prevent electrical accidents. Firstly, qualified personnel with specialized training and experience should perform all work on high voltage systems. Secondly, appropriate personal protective equipment, including insulating gloves, sleeves, and footwear, must be worn to protect against electric shock. Thirdly, lockout/tagout procedures must be followed to de-energize and isolate the circuit before any work is performed. Fourthly, grounding practices must be implemented to minimize the risk of static discharge and fault currents. These practices may include the use of grounding rods, grounding mats, and bonding conductors. Fifthly, regular inspections and maintenance should be conducted to identify and address any potential hazards such as damaged insulation, loose connections, or corroded components. Sixthly, electrical codes and standards such as the National Electrical Code (NEC) provide detailed requirements for the installation, operation, and maintenance of high-voltage systems. These codes and standards are designed to ensure the safety of personnel and equipment. Proper grounding is essential for protecting against electrical hazards in high-voltage systems. Grounding provides a low-impedance path for fault currents to flow back to the source, allowing protective devices, such as circuit breakers and fuses, to quickly interrupt the circuit and prevent damage or injury. Grounding also helps to reduce the risk of static discharge and voltage transients, which can damage sensitive electronic equipment. There are several different grounding methods that can be used in high-voltage systems, depending on the specific application and design. These methods include solid grounding, resistance grounding, and reactance grounding. Solid grounding provides a direct connection between the neutral point of the system and ground. Resistance grounding introduces a resistor in the grounding path to limit the magnitude of fault currents. Reactance grounding introduces a reactor in the grounding path to limit the rate of rise of fault currents. The choice of grounding method depends on factors such as the system voltage, the available fault current, and the sensitivity of connected equipment. Insulation is another critical aspect of high-voltage systems. Insulation is used to prevent current from flowing between conductors or between conductors and ground. The insulation level of a conductor or piece of equipment must be sufficient to withstand the maximum voltage that it is likely to encounter. The insulation level is typically expressed in terms of a voltage rating, which indicates the maximum voltage that the insulation can withstand without failing. There are several different types of insulation materials that can be used in high-voltage systems, including polymers, ceramics, and liquids. The choice of insulation material depends on factors such as the voltage level, the operating temperature, and the environmental conditions. Regular testing and maintenance of insulation are essential to ensure its integrity and prevent failures. Insulation resistance testing, also known as mega testing, is a common method for assessing the condition of insulation. This test involves applying a high voltage to the insulation and measuring the resulting current. A low insulation resistance indicates that the insulation is damaged or contaminated and needs to be repaired or replaced. Corona is another phenomenon that can occur in high voltage systems. Corona is a partial discharge that occurs when the electric field strength around a conductor exceeds the dielectric strength of the surrounding air. Corona can cause audible noise, radio interference, and ozone production. It can also erode insulation and lead to premature failure of equipment. Corona can be minimized by using smooth, rounded conductors and by avoiding sharp edges or points. Shielding can also be used to reduce the electric field strength around conductors and prevent corona. Surge protection is another important consideration in high voltage systems. Surges are transient overvoltages that can be caused by lightning strikes, switching operations, or equipment failures. Surges can damage or destroy sensitive electronic equipment. Surge protection devices, such as surge arresters and surge suppressors, are used to protect equipment from surges. These devices divert the surge current to ground, preventing it from reaching the protected equipment. Surge arresters are typically installed at the entrance to a building or substation to protect the entire electrical system. Surge suppressors are typically installed at individual pieces of equipment to provide localized protection. Harmonics are another potential problem in high voltage systems. Harmonics are sinusoidal voltages or currents that are integer multiples of the fundamental frequency. Harmonics can be caused by nonlinear loads such as electronic equipment and adjustable speed drives. Harmonics can cause a variety of problems, including overheating of equipment, reduced power factor, and interference with communication systems. Harmonic filters can be used to reduce the levels of harmonics in the system. These filters consist of capacitors and inductors that are tuned to specific harmonic frequencies. Power quality is an important consideration in high voltage systems. Power quality refers to the characteristics of the voltage and current waveforms in the system. Poor power quality can cause a variety of problems, including equipment malfunctions, reduced efficiency, and increased operating costs. Power quality can be improved by using power factor correction equipment, harmonic filters, and surge protection devices. Monitoring of high voltage systems is essential for ensuring their safe and reliable operation. Monitoring can be used to detect potential problems before they lead to equipment failures or safety hazards. Monitoring systems typically collect data on voltage, current, power, temperature, and other parameters. This data can be analyzed to identify trends and anomalies. Alarms can be configured to alert operators to potential problems. Maintenance of high voltage systems is essential for ensuring their long-term reliability. Maintenance activities typically include inspection, cleaning, testing, and repair. Inspections should be conducted on a regular basis to identify any potential problems. Cleaning should be performed to remove dirt, dust, and other contaminants that can degrade insulation. Testing should be performed to verify the performance of equipment. Repairs should be performed to correct any problems that are identified. Training is essential for personnel who work on high voltage systems. Training should cover topics such as electrical safety, grounding, insulation, corona, surge protection, harmonics, power quality, monitoring, and maintenance. Training should be provided by qualified instructors and should be updated on a regular basis. The design of high voltage systems is a complex process that requires careful consideration of many factors. These factors include the voltage level, the current capacity, the grounding method, the insulation level, the surge protection requirements, the harmonic content, the power quality requirements, the monitoring requirements, and the maintenance requirements. The design should be performed by qualified engineers who have experience in high voltage systems. Installation of high voltage systems must be performed in accordance with applicable codes and standards. The installation should be performed by qualified electricians who have experience in high voltage systems. The installation should be inspected and tested to verify that it meets all requirements. Operation of high voltage systems must be performed in accordance with established procedures. The operation should be performed by qualified operators who have been trained in the operation of high voltage systems. The operation should be monitored to detect any potential problems. Troubleshooting of high voltage systems requires a systematic approach. The troubleshooting should be performed by qualified technicians who have experience in high voltage systems. The troubleshooting should be based on a thorough understanding of the system and its components. The troubleshooting should follow a logical process of elimination to identify the root cause of the problem. Repair of high voltage systems must be performed by qualified technicians who have experience in high voltage systems. The repair should be performed in accordance with established procedures. The repair should be inspected and tested to verify that it has been performed correctly. Safety is the most important consideration when working with high voltage systems. All personnel who work on high voltage systems must be trained in electrical safety and must follow established safety procedures. All work on high voltage systems must be performed with the power off unless it is absolutely necessary to work on live equipment. If it is necessary to work on live equipment, special precautions must be taken to protect personnel from electric shock. The NEC provides detailed requirements for the safe installation, operation, and maintenance of electrical systems, including those operating above 2000 volts. These requirements cover a wide range of topics, including conductor sizing, overcurrent protection, grounding, wiring methods, and equipment installation. Compliance with the NEC is essential for ensuring the safety of personnel and equipment. Understanding the voltage reference, whether it's voltage to ground or voltage to voltage, is paramount for safe and effective operation of electrical systems above 2000 volts. Consulting relevant electrical codes and standards, as well as seeking guidance from qualified professionals, is highly recommended when working with high voltage systems.